Hello, everybody. A very warm welcome to the second Nuclear Masterclass webinar. It's great to see so many of you in the audience. I think we're just approaching 230 people here live, so that's fantastic. Welcome, everybody. For those of you who weren't here last week, I'm Dr. Elizabeth Cunningham, a former nuclear physicist, now science communicator and Lego enthusiast. Fan of the Binding Blocks project run here at York. I'm excited to be with you here tonight to chair what I know is going to be a wonderful webinar with our fabulous speaker. Okay, so I think that's the formal introduction over and done with. So now we can move to the main event. So we are absolutely spoiled with tonight's speaker. Arnau is here to talk to us. He's a theoretical nuclear physicist and associate professor at the University of Barcelona, and he is one of the nicest people in the universe. So he's going to give us an excellent talk today. In his talk tonight, he's going to take us into the realm of stellar corpses and zombies. We're going to walk through the stellar cemetery, finding out what happens to stars after they have run out of nuclear fuel. So it's my great pleasure to hand over to tonight's speaker, Arnau.
Thank you very much, Elizabeth. I hope you can all hear me and see my screen. My name is Arnau Rios. As Elizabeth just said, I'm a theoretical physicist here at the University of Barcelona. I was for a long time a theoretical physicist at the University of Surrey. And it's my great pleasure today to discuss and about some of the most extreme astrophysical systems, stars that are out there. And in particular, I will try to take a grave through what we call the stellar cemetery, and not just see corpses, but actually see zombies walking around. So I'm going to try. So the aim of the talk today is really to explain what I mean by zombies, to explain what I mean by degenerate, and all of these while talking about stars and nuclear physics, which is what you guys are all learning in the nuclear physics masterclass. I'll start by talking about zombie stars. I don't have really the time to talk about all the possible zombie stars, so I will focus on my favorite type of zombie stars, which are neutron stars. And I will also try to tell you that what we learn from those stars is also very useful to us, specifically to nuclear physics, about and science in general. Good. I'll start with a bit of a preliminary, trying to settle some concepts and some ideas. I need at least 4 different ideas today to tell you about what zombie degenerate stars are. The first of 3 concepts are sort of easy. They are particles you should all know about. These particles show up in things like the atom. So here you have a picture of the helium atom. The helium atom is most of its size comes from the electronic cloud. There's 2 electrons in the helium atom, and these electrons are some of the particles that I will be talking about today. But of course, inside of the helium atom, you have the helium nucleus. It's much smaller than the atom. So if the atom is a football stadium, then the nucleus is an apple or maybe the football. And these nuclei are formed by 2 sets of particles, the neutron and the proton. So today I will be talking mostly about how we can make stars out of only electrons and neutrons. And those are some of the types of zombie degenerate stars that I will be discussing. The 4th concept that I need to convey today is what is the mass of a star. And by the units that are used in astronomy are sort of obviously based in our observations of stars. And of course, our closest star is the sun. And so if we're talking about how much a star weighs, then we typically do this by comparing it to the sun. And so here you have a picture of the sun, beautiful star, of course, from close by. This is, by the way, from the Astronomy Picture of the Day website. If you are not signed up to it, do, because you always get very, very neat pictures every morning on different astrophysical aspects. So what is the mass of our sun? It can be measured in different ways. I'm not going to go into that. It's more or less this number that you have down here. It's a 1 followed by 30 zeros. So it's a very big mass. It's 10 to the 30 kilograms, right? It's a unit of measure that I will be using from now on, and you will see that for neutron stars, for instance, you have things that are more or less the same mass as the sun, but that can be much, much smaller. So just keep that in mind: electrons, neutrons, mass of the sun, 10 to the 30 kilograms. Right. So as Elizabeth said, I want to talk about the end, what happens at the end of the life of a star. But maybe we should really consider, first of all, what is the life of a star? No? What do stars do? So a star like the sun, as we have just seen, is actually a system that is in equilibrium. You have two competing forces. You have gravity that is trying to pull this 10 to the 30 kilograms, so a lot of mass together. Gravity always takes mass and brings it closer or makes it attractive. It tries to pull all that mass together to the center, but there is something that is stopping gravity from collapsing the system, from making it smaller. There's something that is counteracting the effect of gravity, and that something is pressure. And we all know what the pressure is when we wash our hands with water. That's water making pressure on top of us. So here, the fluid of the star has a source of pressure at the interior, and this comes from the temperature that in turn comes from the fusion reactions at the center of the sun. In fusion reactions, you take, for instance, 4 protons and convert them into a helium atom. This process generates energy. Energy gets transformed into heat. Heat is temperature, and this generates pressure. For a system, for the sun, for instance, this fight between gravity and pressure is very well equilibrated, and it can last for as much as 10 billion years. So it's a very long time in which the star is doing this. But of course, at some point, if the fuel that is running the life of a star are the hydrogen or the protons at its center, then it's only natural to ask what will happen when this fuel is exhausted. What happens when you don't have any more protons to fuse? Eventually, you release this source of pressure, and so something must happen. Well, that's exactly what we mean by the death of a star. So the life of a star is all the time that the star spends in this equilibrium state, fusing protons and providing temperature to fight against gravity. But then at some point you lose your fuel and something happens, the star dies. And how a star dies really depends on a single parameter, more or less, which is its mass. So we've already talked about the stellar mass. And depending on the mass of the star, there are different fates that this star can suffer. And so here you have a diagram of the different types of star as a function of their mass. Going up here and going towards the right, you have the different fates of stars. So for instance, if I look at stars that are more or less like the sun, maybe a little bit smaller, maybe a little bit larger than the sun will live, as I said, for maybe 10 billion years. It will eventually become a red giant, go through a nebula phase, and eventually become a white dwarf. When you look at stars that are a bit heavier than the sun, maybe 10 to 25 solar masses, you get that the end point of the revolution, that they also go through a red giant phase, but the end point of the revolution is slightly different, and it's a neutron star. And we believe that anything that is about 25 to 30 solar masses or heavier will end up its life as a black hole. And so, as you can already see, the stellar symmetry, the ways in which stars die, is very different. There are several different outcomes to the life of a star, or if you want, different ways of dying for stars. So I will mostly focus on these two types of stars, neutron stars and white, or death stars, neutron stars and white dwarfs in this talk. And just to be clear, I'm talking about the death of a star, not the Death Star from Star Wars. Although we will come back to Death Star, to inside the Death Star in a second. So yeah, the end point of the life of a star really depends only on its mass. You have these 3 categories that I've talked about: black hole, neutron star, and white dwarfs. There's also brown dwarfs, which are things that are much, much lighter than our sun. And so you can classify this graveyard or this cemetery depending on when you look at these different types of stars. Brown dwarfs are more like toddlers. They haven't really died. That's a whole different talk that I should give one day to explain what brown dwarfs are. I'm just going to focus on white dwarfs. White dwarfs really are. Oh, sorry. I'm first going to talk about black holes. Black holes are really the end point of a stellar evolution in the sense that there is nothing that you can see from a black hole. So this is, there's no matter coming out of this black hole. There's no light. There is nothing you can see out of it. There is an event horizon that protects everything that is inside this black hole. So this is, in my mind, this is really proper death. White dwarfs, on the other hand, are quite warm. Even though they are dead, they can be very bright. And so they are the end point, or they are dead stars, but they are kind of alive too, because you can see them. And so in that sense, that's why I call them zombies, and very bright zombies, and warm zombies, in fact, because you can see them with your own eyes. Neutron stars, on the other hand, are real, more scary zombies, because they are really not visible with your own eyes. You really need to turn to other ways of seeing those stars, and we will talk about some of those different ways in the next few minutes. Right. So I said stars. Okay, so at the end of the life of a star, you run out of fusion reactions. There's no more protons. So how is it that you can have these zombie stars? How can they exist? If there is nothing that is stopping gravity from working, how do you generate an object in the sky that is maybe bright as a white dwarf, or that is maybe visible in radio waves like we will see with neutron stars? What is stopping this collapse if there is no temperature? Right? And the answer to this question is already in the title of this slide and in the title of this talk. It's something called degeneracy. Right? Now, degeneracy is a really bad word. If you go to the dictionary, it will tell you that degenerate means having lost the physical, mental, or moral qualities considered normal and desirable, or showing evidence of decline. Here's a picture of degenerate Jack Nicholson in The Shining. But in physics, degeneracy means something slightly different. So let me try to explain what degeneracy means and how this sort of and how you can actually obtain a pressure source out of quantum mechanics, which is exactly the definition of degeneracy in physics. To do that, I'm going to do a thought experiment, a little bit like Einstein would do. Think about an exceptional situation. My exceptional situation happens inside of the Death Star. You've all seen this movie. You've all seen this scene. The garbage compactor. Luke, Leia, and Han Solo are trapped, and suddenly the walls are shrinking and shrinking, right? At some point, Luke and Leia escape. So there's no people in here. Now there's only matter. And let's think about what would happen if this compactor would keep on compacting the matter inside, right? Of course, things would get shrunk and shrunk and shrunk. Imagine that we had a compactor that was extremely strong and that you could keep on compacting and compacting, right? That's the thought experiment that I'm thinking about. So if you look at the matter inside of here, what will happen is that this matter will become degenerate, right? The way you can think about this is that when you have, for instance, a gas or the matter inside of the degenerate compactor, it is more or less flying around. There is some motion coming from temperature. Particles are bouncing up and down. If you keep on compacting, maybe you generate a plasma or something like this. Matter will, these particles, electrons, neutrons, protons will be flying all over the place. But then as you keep compacting, at some point, it's unavoidable that you will reach a situation in which those particles won't have much more space to move. And in that situation, you enter the realm of quantum mechanics. And the description in which, because there is no more thermal motion, the description of the particles inside of the compactor needs to rely on quantum physics. And at this stage, we know two things about quantum physics that help us explain what happens in this degenerate environment inside the trash compactor at very small length scales. On the one hand, we have the Heisenberg uncertainty principle. This was Bernard Heisenberg was one of the creators of quantum mechanics, and in 1925 he came up with this idea that if you have a very small uncertainty in position, it turns out that then this means that you must have a large uncertainty in momentum because the product of the uncertainty of the position and the momentum is larger than a given quantity, Planck's constant, right? So if you have very small uncertainty in position, as you would have in a trash compactor that is extremely, 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 extremely narrow, atomically narrow, then the particles would necessarily acquire something called momentum, which is basically motion. So particles would start moving around. In addition to that, we also have a second principle of quantum mechanics that is key in this situation, which is the Pauli exclusion principle. Perhaps some of you have heard about this. This is the same thing that creates the atomic table, for example, in chemistry, because this is telling you that two electrons in an atomic cloud cannot occupy in the same state. In this situation, what this means is that two electrons really don't want to sit in the same position inside of the Gedanken experiment of the trash compactor, and as a consequence, they will, because they won't be sitting in the same position, they will acquire momentum. Momentum means motion, and motion means pressure. And so immediately at this point, even if you try to keep on compacting the matter, quantum mechanics would stop you from doing this because the Pauli exclusion principle would act as a source of pressure. So this is a source of pressure that would try to stop the collapsing walls of the trash compactor, and it's independent of the temperature of the system. It really only depends on the scales, on the length scales on your system. And so what happens inside of a star, like a neutron star or a white dwarf, is that a source of pressure at the interior that is stopping the collapse is purely quantum, and it's associated to this degeneracy effect. The new electrons, for instance, inside of a white dwarf feel the pressure compacting them of all the matter outside of the white dwarf. This is acting like the trash compactor of the Death Star, except that it's the actual matter of the star that is acting with this pressure, and then they immediately counteract this incoming gravitational pressure with quantum mechanics. So neutron stars, on the other hand, it's not electrons that is stopping this degeneracy collapse, it's actually neutrons. And so you can already immediately see that whereas electrons have charge and hence can be bright because they interact with light around them, neutrons don't have any charge, and so they won't generate any light or interact with light in principle. And so that makes them harder to observe, right? So hopefully that has been a nice introduction on what zombie stars are. We are going to be talking about neutron stars now. I will have to forget, unfortunately, about white dwarfs. That would be a whole other seminar for another day. And so I'm going to briefly introduce what a neutron star is, how it was, and how it was discovered, because it's a very interesting story in itself. Neutron stars, just as a recap, they are generated at the end of the life of a star that is maybe between 10 to 25 solar masses. They themselves have masses of the order of about maybe 1 to 2 solar masses, so they are as heavy as the sun, but they are much, much, much smaller than the sun. Here you have a picture of what a neutron star would be in size as compared to York. And so you can see it's more or less the same size. The radius is about 10 kilometers. What this means is that you are putting an immense amount of matter into a very, very small space. This is the smallest star, or in fact, astronomical object that you can think of, something that is only 10 kilometers in size. Compare that to the Earth, which is 6,000 kilometers, or the sun, which is much, much bigger, right? And so you can measure the amount of how much mass there is here inside of one of these, inside of a neutron star, by taking the ratio of the mass to its volume, the so-called mass density. If you do that with the back of the envelope calculation, you will obtain a density, which is 10 to the 17 kilograms per meter cube. That's, again, 17 zeros of kilograms for a meter cube. That doesn't tell you much. It's just, a very large number. This also means that you have more or less about 1 proton per femtometer, so 1 proton for every 10 to the minus 15 meters. Also, so this is more or less the same amount of protons that you have inside of nuclei, or the same amount of density, as you will see in a second. But just to convey this in more layman's terms, what this means is that if you could take a spoonful of material of this neutron star, the spoon would weigh a ton, right? So it would be essentially impossible to do. You would definitely break up the spoon. Although, in fact, just don't try the experiment, because getting close to a neutron star has its own many other dangerous effects other than breaking spoons. And the reason that myself, I'm interested in neutron stars is that the only other place in the universe where you have matter which is as dense as in the interior of a neutron star is in the interior of nuclei. What I'm showing here is this very same quantity, the amount of matter per unit of volume inside of a nucleus, like lead-208, 208 neutrons and protons living stably together. And what you can see is that in the interior of this nucleus, you get at least a number that is very similar to that you get in a neutron star. So if you want to understand the interior of a neutron star, one thing that we nuclear theorists do is compare that to the interior of, say, lead or other nuclei, and then try to use the same ideas that we do in describing nuclei to describe neutron stars. Good. So I promised I would talk about the history of neutron stars. Neutron stars were predicted in 1934 by these two gentlemen here, well-known astrophysicists, Walter Buddy and Fritz Zwicky. The extraordinary part of this story is that the neutron had only been discovered 2 years before that. We're talking about the world in the 1930s, no cell phones. Of course, communication went much slower, but it was not only communication, it was the revolutionary idea of thinking about a new particle discovered a few months earlier, and then thinking, well, maybe these new particles could form stars, and even explaining that this could happen after a supernova explosion, which is exactly the same explanation we have for neutron star formation today. So it's quite extraordinary that these two gentlemen could manage to come up with this idea and publish it in 1934. Now, the idea that was a nice idea, it was taken by astrophysicists, but immediately was kind of forgotten, because, as I said earlier, neutrons don't really have a charge. If they don't really have a charge, it means that light can more or less go through them without interacting. There is nothing affecting them in the electromagnetic spectrum, which means that they won't be shining, and so we shouldn't see them. Also, they are very, very small, 10 kilometers. So, it's going to be a very dark object or very cold object, very dark, sitting very far away. There's probably very few chances that we would see them at all. And this was the situation for about 30 years. So the neutron stars were predicted here in 1934. And the first neutron stars were discovered in 1967 when somebody found a pulsating radio source in the sky, and then just a few months later, it was realized that the only object that could create something like that pulsating radio source, was a neutron star. And so, okay, so what happened? Who discovered this pulsating radio source? So this is a very nice story of a very young PhD student, Jocelyn Bell Burnell. You can see her sitting here next to a field of antennae in Cambridge. In 1967, radio astronomy was already a blooming field. Since the 1930s, people have been pointing radio telescopes or radio antennas to the sky to try to see where you could see radio sources coming from from outer space, essentially. What was new in the PhD thesis of Jocelyn Bell Burnell was that the technology was developed and was good enough at that point to look at the change in time of the radio waves coming from outside of the Earth. Right, so you could point, well, you couldn't really point, as you can see. It was really a field of antennas, but as the Earth was rotating, it would sweep by the sky, and you could hear changes in the radio sources, right? And in the 6th of August of 1967, Jocelyn Bell Burnell discovered this source here that was pulsating with about a period of 1 second. So every second, there was a dip in the radio signal. She went back to her supervisor, Anthony Huish, and asked, well, what could this be? I'm seeing clearly something in the sky. It has a pulsation of 1 second. They started looking for possible sources. Maybe it was a radio antenna somewhere else on campus. It wasn't. Maybe someone is emitting at this radio frequency with this period somewhere else in the country. It wasn't in the country. It was the 1960s. This was the Cold War. They thought maybe it was the Russians, maybe it was somebody else, but all these hypotheses went on dying relatively quickly because this was a source that was outside of the Earth, very far away, pointing in and being with this frequency. So at some point they ran out of options, and so they started calling this thing, well, Anthony Hewish, Jocelyn Bell Burnell supervisor, started calling this thing LGM, which stands for Little Green Men. Because, of course, you see a period, some sort of signal coming from the sky like this, and you think maybe this could be an extraterrestrial source. Incidentally, they were about to tell everybody that this was the case, that aliens had finally contacted us, etc. They breach every single rule in the SETI protocol. So just in case, if you ever find an alien, you should know there is a protocol that you should follow. It's the SETI protocol. They were about to basically breach it completely and announce widely that they had seen little green men. But then something extraordinarily happened, and it was that Jocelyn Bell Burnell discovered a second source on the other side of the galaxy, emitting more or less with the same frequency or with the same period. And so immediately this meant that this couldn't be really extraterrestrial beings because because a periodic signal doesn't really carry any information, so that's not something that you would send. And also it would have to be civilizations that would be in touch across the galaxy, extremely far away, to the point that it was totally unlikely. This must have been some sort of new star, right? And so Jocelyn Bell Burnell was very happy. She got her PhD. She was only 24 at the time, by the way, so that's an important message for all of you young people. You still have, you can make interesting scientific discoveries when you're very young. And unfortunately, her PhD supervisor, Sir Anthony Hewish, got the Nobel Prize. That's Jocelyn Bell Burnell explaining the same story that I just explained. She was only 24 years old at the time, but he got the Nobel Prize in 1974. Something that didn't really change, or that was really a dismissal of her contribution, in fact, and that was only fixed recently, about 10 years ago, when she received the Breakthrough Prize in Physics, which is even more money than the Nobel Prize. So that was very good. And of course, I should just point out that Jocelyn Bell Burnell is only one of the many women that have contributed to science that we don't usually hear about. Women in Science Day was only a few weeks back. And so I just want to point out that there's a lot of other predecessors of Jocelyn Bell Burnell that made outstanding contributions to science. And if there are any young girls listening still, please think that you can be one of them in the future too. Right. Pulsars were immediately taken over. There were a lot of pulsating radio sources coming from the sky. As I said, the only really plausible explanation of what a pulsar could be were neutron stars. They are very small objects. They probably rotate very fast. I'll explain that in a second. In 1974, another pair of PhD student and supervisor were observing radio waves with this telescope, the Arecibo telescope in Puerto Rico, unfortunately shut down a few months ago. And they found a very curious signal of two, not just one, but two neutron stars orbiting one another, right? Again, Russell Hulse here was 24 years old. And in this case, this discovery was extremely important to the point that it got them the Nobel Prize in 1993. And the reason this was really important is that these two neutron stars sitting together had extremely large gravitational fields, and they could be used to prove a theory by Einstein called general relativity, which is how we now understand that gravity works in extreme regimes. And whereas Einstein had proved this right with a very small effect and modification of Mercury around the sun, these two guys could manage to actually find an effect that corroborated general relativity's quality or the effects predicted by general relativity with a very large quality in 1974. And this got them the Nobel Prize. Here you have a plot of this effect of general relativity. The theory is the blue line, and the red dots here are the different measures of this pulsar, binary pulsar of Halls and Taylor. And as you can see, they follow exactly the same line as general relativity. So pulsars were, neutron stars, in fact, were actually very important also in corroborating theories of gravity like general relativity. Now, I've said that these are pulsating, neutron stars are pulsating radio sources. What do I exactly mean by that? How does this pulsation work? Well, you have to imagine that you have a neutron star, which is about 10 kilometers inside, and that it's rotating. For reasons that I cannot really go into detail now, but it also turns out to be that neutron stars have the largest magnetic fields in nature. And if by any chance, in the way in which these neutron stars are born, the rotation axis is not aligned with the axis of the magnetic field, so if the north pole of the star is not pointing in the same direction as the rotation axis of the star, something that happens in Earth, but with a very small angle. In neutron stars, it can happen with a much larger angle. Well, these very large magnetic fields immediately kick off any charged particles like electrons or protons outside of the neutron star, generating a radio wave, a collimated radio source, which is a very narrow source of light, but very intense. If as this star rotates, this small collimated beam hits the Earth, you will see it as it rotates as a small blip every time that the star rotates and that the beam sweeps the Earth. And that's exactly what you see for different pulsars. You see pulses that are separated by maybe a few seconds. Each pulse can be different, but when you average the pulse for every neutron star, you have an individual signal that in fact it's a fingerprint of the pulsar itself. Right? So the pulsation has to do with the misalignment between the rotation axis and the magnetic field, north pole of the star, sweeping over Earth. Right? Now, it's a radio wave, so some people at Jodrell Bank, the radio observatory near the University of Manchester, had the brilliant idea of taking these radio signals and actually putting them through a radio speaker. And so hopefully this will work, and you will, guys, now will hear a neutron star signal. So really the music coming from one of these stars, right? I'm going to start with this one, which is a video of about 1 second. And I use the you expect every second the pulse of light, radio light from the next one is going to be the crab pulsar. This is slightly faster. It's about 30 hertz. So times per second, so it's a bit faster. It sounds a bit more like maybe a helicopter. And then finally, maybe you have to lower your volumes a little bit because we are now going to hear a millisecond pulsar, something that is much faster. Really annoying sound. Sorry about that, guys. But what I want to convey is that this is sound coming from the stars. So, when next time that you look at stars, of course, you can always look at stars with your own eyes. That's exciting. But think about the fact that there's also sources of radio waves out there that you can hear as well, which I think is quite extreme. Sorry about that. Okay. Fine. So what do we learn about neutron stars? Well, some of the things that we can measure have to do with, for instance, having two, not one, but two neutron stars together, or one neutron star and another star. If this happens, typically these two stars will orbit each other, and this orbiting will make the pulsar wobble in a very specific way. This wobbling, because the pulsars are very precise emitters of radio waves, this wobbling can be measured, and this wobbling of the star can actually help you weigh the star and find out its mass. This is rather extraordinary. And so here what you have is a handful of tens of neutron stars that are in binary systems. So a neutron star together with another neutron star or with another star, for which we have been able to measure masses. Right? And you can see here that the typical masses are between 1 and 2 solar masses. That's already quite impressive, the fact that you can measure something with this quality. But some of them, and you can see that some of them have relatively large error bars. Some of them have very small error bars, though. And so if I go back to the Hulse-Taylor pulsar, which is exactly this black dot here, it's not that there is a mistake and we have forgotten the error bar here. It's that the error bar, that these measurements coming from the wobbling of the neutron star are so precise that the error bar you cannot really see inside of this dot. So the Hulse-Taylor pulsar weighs 1.438 solar masses with a precision that is 0.001. Right? I mean, and think about it. So this morning I actually went and donated blood and I had to give my weight. And I very often forget really what my weight is, or maybe, approximately to the 3 or 4 kilos, right? In Spain, probably in the UK, you guys weigh what? Around 100 pounds. I mean, if you go weigh yourself, maybe your balance has an error of 1, 2 pounds. That would be the third digit here. This is a star which is sitting across the other side of the galaxy. And what these measurements of the wobbling of the star allow you to do is measure its mass with way more precision than you measure yourself with a balance every morning, or hopefully not every morning, but at least every now and then, right? So it's quite an extraordinary feat that you can do that with radio astronomy and radio measurements. And the information that you get from this is really, really extraordinary. For instance, although I won't have much time to talk about, the fact that there is not many stars up here or beyond 2 solar masses is an indication that these stars are also made of neutrons and protons, and this is a very strong constraint on the way in which we understand how neutrons interact with themselves, because most of this matter, of the matter inside of neutron stars, would be formed by just neutrons. Right. So neutron stars as extreme laboratories, they are the densest stable systems and largest in the universe. We can measure their mass and their radii. They are extraordinary because they have the highest magnetic fields in the universe. This is what generates the radio pulsars. They are extreme gravity laboratories. They also are superfluid and superconductors. I don't really have time to go through this, but these are really extreme quantum properties that show up and only show up in these stars as well. So that's quite cool. And finally, I just want to give a brief notion that while we observe neutron stars with radio waves, we also observe them with a different type of wave that was discovered more or less about 10 years ago. I still remember the day that this happened. It was February 11th, 2016. I was at the University of Surrey, and all of us went to watch the live release, press release of how two black holes had been discovering, coalescing each other using gravitational waves. Now, gravitational waves are a different type of wave. They are not sound waves. They are really waves that travel across space-time. It's very hard to measure them. This initial discovery was done by the Laser Interferometer Gravitational Wave Observatory, LIGO. LIGO has 2 sites in the US. One is in Hanford and the other one is in Livingston, as you can see, across the US, very long distances from each other. And each one of these 2 observatories has more or less this L shape with 2 arms of 4 kilometers. These interferometers have laser light going through and bouncing back and forth these 2 Ls. This allows them, this bouncing back and forth allows to measure small deviations in length of the order of the size of a proton. So this is 4 kilometer objects measuring changes in the gravitational field and in the nature of space-time, which is smaller than the size of a proton. So this was an extraordinary feat to be able to measure this. And the waves that we can measure with these types of observatories are exactly the types of waves that come from, for instance, the coalescence of two black holes, but also the types of waves that come from the coalescence of two neutron stars. And so what I'm showing you here is the waveform or the type of wave that you can measure from two black holes. These five objects here on top are different black hole combinations. As you can see, the signal for the gravitational waves lasts for about 2 seconds in this case. When you have the case of two neutron stars orbiting together, the waveforms are actually much different and they take much longer to evolve. I'm actually going to fast forward this because by the time you get to the about a minute, you hear this blip. Again, this is post-processing the gravitational wave signal and getting into the radio. But this gravitational wave beep tells you that these two neutron stars have merged. They have formed another object that is spherically symmetric. It could be a black hole or it could be a neutron star. And this small blip also carries a lot of information about what these neutron stars are. And for instance, in this case, in this one specific case for gravitation, for this object GW gravitational wave 170817, these neutron stars had about 1.4 solar masses, the same type of mass that you can measure with radio waves. So that was quite extraordinary. This event was extreme. So this happened on the 17th of October of 2017. It's so far the best observed binary neutron star system that has been seen with both gravitational waves and all the other telescopes. In fact, the gravitational wave was detected first, and within about a day, most of the telescopes of the world were looking at the place where this explosion took place or where this binary neutron star merger took place. And then just to close, I want to show you how the graveyard of stars or objects looks like when you look at it from gravitational waves. And to give you some bad news, everything that you see here, or most of the observations that you see here, are these blue dots. These are mergers of two black holes. So two black holes merging together in gravitational waves. There's only a handful of neutron stars that have been observed with gravitational waves. These are the orange blobs in here. You see that I'm quoting 35 here. This is when this picture was taken at the end of the third run of the LIGO observatory. This picture has changed actually. There is no new picture yet because this only happened on Thursday. But on Thursday, a new release of all the data of the gravitational wave observatories came out and has pointed that there is actually 129 black hole binaries that have been observed, but unfortunately, only two neutron star binaries have been seen with enough quality to tell us something. So I'm really looking forward to the next generation of observatories of gravitational waves that hopefully will be able to detect more of these neutron stars and tell us something about how neutrons and protons behave inside of the extreme matter of neutron stars. And so I'm probably going to close it there, leave this picture of a neutron star from you. This is a very famous picture by a very famous British band, and it represents really the spectrum of a pulsar. And with that, maybe we can go to the questions, Elizabeth.
That was wonderful. Thank you very much. Yes, I think we do have to stop there. We've got a lot of questions and I want to try and get through as many as possible. But I just want to say thank you very much for that fascinating talk. I really enjoyed the beat you took to talk about female contributions to the story. I less enjoyed the noise, the spine tingling noise from the pulsars. Um, but yes, no, very good, excellent. Okay, so I'm going to warm you up with a nice question. So someone has asked if the mass of a star is heavier, does it tend to live longer or a shorter amount of time than one
Oh,
with smaller mass?
That's a very good question. And in fact, how long a star lives is also determined by its mass. Typically, much heavier stars live a shorter life, whereas a much shorter life, in fact. So if you have a 10 solar mass star, for instance, it would only live a few million years instead of few billion years.
Very good. There's a few questions around sort of the life cycle of stars. So there's a question. There's two questions. There's one which is connected. There's one that's the process through which the remains of is there a process through which the remains of dead stars can be recycled into new stars, or will there at some point be no stars? And that's connected to what will happen when all stars become dead. Where will the energy go? Will life be possible? Is it possible that the universe will collapse and the Big Bang will happen again? So, sort of, what happens if will the stars all go out
Right.
and can they be
Exactly.
recycled?
Yeah, yeah. Okay. So maybe I'll start with the recycling bit. Yeah, there's all kinds of things that can happen. Sometimes you have as I said, you can have two stars close together, a neutron star and another star. This means that these two stars were together before. So at some point, one generated a neutron star, the other didn't. The matter from the one star can fall inside of the neutron star too. This generates something called X-ray burst, and new explosions. This generates new elements that are very hard to produce otherwise. So yeah, I mean, you have a lot of, I've explained this very briefly, but there's a lot of different things that can happen when you have one star, and even more exciting things that can happen when you have two of these stars together. Now, on the pessimistic side, it's true, eventually, in a very, very, very long time in the universe, most of the stars will have exhausted their fuel. The neutron stars that will be out there also, I haven't really mentioned that, but they are hot but cooling down because there's no way to generate any energy inside of them. This that same thing with white dwarfs. So everything will eventually probably cool down, and we will be in a very boring, dark universe. But don't worry about this because it's going to happen in such a long time that many, many civilizations will have happened before that.
Thank you very much. So we have lots of questions about degeneracy and quantum mechanics. So I'm going to start by asking that someone's asked a very simple question. What is quantum mechanics in simple terms? I don't quite understand.
That's
And
a
we,
very good question.
we'll build on to the other questions. Yeah.
Yes. So quantum mechanics is generally explained as the theory that describes the smallest things in the universe, things like atoms, like nuclei. There, the laws of physics, as we understand it, for big objects or for macroscopic objects like us, Newtonian mechanics that explains gravity or how the apple falls. Some of these things break down when you go to the microscopic scale or to the atomic scale. And so you need a new theory to explain this. This is what quantum mechanics is. So it's a different way of understanding physics that generally applies to the smallest things in nature. The cool thing about degeneracy, though, is that it tells you that there are also stars that rely on the existence, whose existence relies on quantum mechanics too. So it's not really only the small things that are affected by quantum mechanics. Sometimes there's big things that also are.
Okay, so I think we're leading on to questions about that. So someone has asked, are degenerate particles just particles compacted enough so they operate under quantum mechanics?
Perfect definition. I should steal
Wonderful.
that one. I should steal that one. The next
Or
time.
we can send you the questions afterwards.
Absolutely.
Someone has asked slightly more a similar question, slightly more technically, saying is quantum degeneracy pressure purely generated from the Pauli exclusion principle, or also from electrostatic forces between fermions, negatively charged electrons?
Yeah, it's the Pauli exclusion principle at play. You can have, let's say, that's what plays the biggest role. Of course, if these particles are electrons and then they feel the Coulomb force, this can have an additional contribution because it will also be repulsive. Two negative charges will want to will feel an outgoing force and an outgoing source of pressure too. But that's a correction on top. Really, when you get to the level of degeneracy that you have inside of a white dwarf or inside of a neutron stars, these things are just small corrections. It's the Pauli principle that it's really stopping the collapse.
Okay. Someone would like to clarify, have fermions been proven real or are they still a theory?
Oh, no, absolutely real. Yeah, yeah. Every atom, electrons, neutrons, and protons are fermions. The way that chemistry works, the way that our world works is basically a consequence of the Pauli exclusion principle. So we really know that fermions are out there. Absolutely.
And then this is sort of connected to this discussion. Why usually small forces of quantum mechanics become so influential in a relatively big scale? How does this transition from small to big scale happen?
Yeah, well, that's a very big question, a very good question. You have to think a little bit about um, how to develop uh, these ideas, but essentially, let me see, I'm trying to come up with an analogy. I probably won't. It's really it's really this combination of gravity and pressure. Maybe let me see. Let me go back to the slide of the degeneracy. When you think about a star, you can think about it as formed by very small droplets of matter, and you can then so each one of these droplets, small droplets, is so small that quantum mechanics applies, quantum degeneracy pressure builds on it, and then you can then build up on these small droplets to build the whole star. The way this is done has to do with hydrodynamical equations. And importantly, for neutron stars, there's a set of equations called the Tolman-Oppenheimer bulk of equations that allow you to do that, to go from this microscopic to the macroscopic scale. And I've just flashlighted there the name of Oppenheimer, of course, who was a very famous physicist.
Very good. So there was a few questions that came in when you used the sound files for the pulsars. So someone's interested in how do telescopes pick up the signals and how is the sound from stars recorded if sound can't travel through space?
That's right. It's not really, that's a very good question. You don't really hear this sound coming from space. Famously, you cannot hear because there is no air in space, so there is nothing that sound can travel from. What I showed there, or what you heard there, was the radio signal traveling from the sky translated into sound. And so the intensity of the radio wave was transformed into intensity of sound. This is the same process that you use when you take the radio waves of your standard radio, FM, AM, and you listen to the radio in your car. It's the same process, except that the signal that you're looking at, it's not emitted by an antenna, but it's emitted by that star. So what you're really hearing there is a translation, if you want, of radio signals to sound signals. The way that these telescopes work, I mean, they're basically very big antennae. I mean, we've all seen small satellite dishes like the ones that you have to watch TV at home. Well, these are much larger in scale, maybe, tens to hundreds of meters big. Uh, they Sometimes they move and they rotate. You can point them to the sky and then you just leave them there and wait for the radio signals to come in. And as I said, for the case of neutron stars, you have to look at radio signals that change over time.
Very good, thank you. Someone has asked, what do you mean by a star glitching?
Ooh. Yes, that's a difficult phenomenon, but essentially, neutron stars pulsate uh, very precisely. They are, in fact, also, in addition to being the densest objects, the largest magnetic fields, they are about the most precise clocks there are. Their rotation is extremely precise. But what happens is that every now and then there is a small glitch in this rotation period. There's something that changes, that wobbles the whole star to the point that the frequency at which it rotates changes suddenly. And these have been observed in a handful of neutron stars, and no one really knows what causes them. The sort of the biggest theory, or the most uh, commonplace theory now, is that there is some sort of a change in the fluid structure inside, of the superfluid structure of the star, that allows them to jump in period, in a sense. But it's very difficult to really understand. Of course, these are very extreme things that are very far away. As I said, they are not really glowing, so You only have a handful of pieces of information that you can rely on to try and understand what their interiors look like.
Very good. Thank you very much. So we had a lot of questions come in as well when you're talking about the discovery of gravitational waves and neutron stars merging. So someone has asked if two neutron stars merged, would it be possible for them to form a black hole?
Absolutely, yes, correct. So maybe I'll go here and I'll explain this. So um, as I've shown, and as you can see also in this diagram here, neutron stars weigh about up until about two solar masses. We think there cannot be anything heavy, there cannot be neutron stars much heavier than this, maybe two and a half, not really three, right? Anything above that has to be, if you see an object in the sky for some reason, maybe orbiting something else, or maybe with a gravitational wave signal like this that is heavier than two and a half, it's most likely going to be a neutron star. So, sorry, a black hole. And so if you have a neutron star of two solar masses, which coalesces with another neutron star of two solar masses, together that makes four solar masses. Four solar masses is too heavy for a neutron star. It's more likely than not going to end up forming a black hole. And in fact, that's what we think happened with this observation, with some of these observations here. You can see this one. They're going blue.
Wonderful. Well, I think this is going to be our last question because we're almost at the end of our time. So I'm going to completely change tack again. Someone has asked, how did you get into your job and what does your day look like?
That's a very good question. My day looks like a combination of what you see back there, which is blackboards and research and thinking about new ideas about, what neutron stars look like in the interior, or using computer simulations to understand that. Sometimes normal computers, sometimes quantum computers now too. And then teaching. So this semester, every week, for instance, every day I have an hour of teaching and I teach maths to physics undergraduates. I talk to a lot of other researchers in the field, here, PhD students, postdocs, my colleagues who work on the same topics or different topics than me. And so it's a very exciting job to be a lecturer at university. How I got here, well, I finished physics as an undergraduate. I was lucky enough to find somebody that decided that I would be a good PhD student and that they could supervise me. After that, I moved away from Spain. This was all in Spain, in Barcelona, by the way. After that, I moved to the US for 2 years. Surrey in the UK for 10, and then a few years back I came back to Barcelona. It wasn't always an easy journey. The academic life can be hard, but it's also extremely exciting when you get to see new discoveries like gravitational waves coming through, new pulsars. It's a life that is full of unexpected pleasures, and so I really enjoy it.
I like that. I think that's a good description of the academic life, full of unexpected pleasures. Very good. Okay, so well, thank you again for joining us tonight. That was a wonderful talk, and you were very good jumping around answering the questions as well. We had loads of questions. I'm really sorry that I didn't get to ask all the questions. I guess all that remains for me to say is to thank Arnau again. Thank you so much for that for that talk, and for answering those questions. Thank you to everybody who's joined us tonight. I hope you've enjoyed your Wednesday evening nuclear webinar, and I wish you all a very pleasant rest of the evening, and hope to see you again next Wednesday. Thank you very much.